Okay, so today we are finishing up chapter 6 with exponential growth and decay problems. And these are word problems, and let's get right into it. So the exponential growth and decay formula, I'm going to really simplify it. I'm going to use the letters A, P, R, and T, 4 variables. A is the final amount. P is principal or the beginning amount. R is our rate, and that's in decimal form, not percent form. And T is our time. Now, E, remember, is Euler's number, or approximately 2.718. It's not a variable. So we have these 4 variables to worry about. So let's start with the bacterial culture of 10,000, which is growing at a rate of 0.6, and our time is in days. Estimate the number of bacteria in 1 week. So I want to estimate my final amount. My beginning amount is 10,000, my rate 0.6, and 1 week, 7 days. So I'll plug all of these variables in, and since I have to just solve for A, I can go to my home screen on my calculator, just type this in, and I will get my final answer. So I always list APRT and then fill in the 3 that I know and solve for the 1 that I don't know. So in this same problem, how long will it take the bacteria to triple in number? So I'm going to end up with 30 if I began with my 10,000 because I want to triple in number. My rate is 0.6, and now they're asking me for time. So I'll plug in the A, P, R, T. Now, to solve this by hand, I would divide both sides by 10. I would take the natural log of both sides. What I do to one side, I have to do to the other. The natural log and E are inverses. Cancel those and divide by 6. So I would have ln of 3 divided by 0.6. Now, when you're putting this in the calculator, ln will have a parenthesis, so you plug in the 3 and close out the parenthesis before you divide by the 0.6. If we want to do the same problem on the calculator, left side goes in y sub 1 and the right side goes in y sub 2, and I always put my exponent in parentheses, so I have 0.6 times, that's just a times x. I used my window. I just went from 0 to 30 because I was looking for time in days. And notice my Y max, I put at 40,000. I really want my Y max to be a little bit bigger than the larger number. So when I graph it, I just get this picture. And if I don't have an intersection, go back to your window and change it. So second calc 5, enter, 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 and I get the 1.83. which would be the same as ln of 3, all divided by 0.6. Okay, same problem. How long will it take to reach 1 million? So I do the exact same thing, changed y1 to 1 million, and I changed my window, intersect, and I get my answer. If I deposit $5,000 in the bank and it compounds continuously at a rate of 7.5%, how long will it take to double my money? Okay, I want to double 5,000, and my rate, notice now I'm in decimal world, 0.075, left side in y1, right side in y sub 2, and change my window, and don't see my answer there. There we go. My answer would be 9.42. In 10 years, how much money will you have in the bank? APRT, 10 years, same rate, same beginning amount. Now notice that this is just an expression, 500e to the 0.075 times 10. And I don't have to deal with y1, y2. I just go to my home screen. This is a home screen problem when you're solving for A. If you're solving for P, R, or T, go to y1, y2. Okay, decay. A radioactive substance is decaying according to our exponential model. The initial amount is 10. 8 grams are going to remain after 5 years. So my A is 8 and my P is 10. So A, P, and my R is what I'm looking for, and my 5 goes in for time. So my R comes out to be ln of 0.8 over 5 if I do it by hand, or on my calculator, I can go ahead and find that. All right, but notice I've been given the P, the A, and the T, and I'm left to find R. Okay, in this same problem, my initial amount is 10. I'm going to use the exact same problem, but now I'm going to introduce half-life. Half-life is a time. Half-life is the time it takes for the final amount to decay to half of the beginning amount. Your final amount is half of your beginning amount. So in my problem, my beginning amount was 10. Half of that is 5. I already found R from the previous example, and they're asking me to find the half-life, which means find the time. So here's my equation. I'm going to put that in my calculator, y1, y2, and I would get 15.54 years. Okay, so now in college algebra, we use A equals PE to the RT, but the notation that you really need to learn, because you're an advanced student now, instead of just A, we use A with respect to time. P is not really the principal P now, it is A naught, the beginning amount. A naught stands for the beginning amount, and rate R is K from now on, okay? So now, this is really nothing more than your PERT formula, just in college. Okay, so traces of burned wood found along with ancient tools. The wood contained about 1.67% of the original carbon-14, and I know that the half-life is 5,600 years. When was the tree cut down? Okay, in this problem, the first thing I need to do is find K. So my beginning amount is A naught. My ending amount is half of A naught. E to the R now is K, and T is time. Divide both sides by A naught, and I'm left with this. ln, both sides, natural log of both sides, divide by 5,600, and I have my rate of decay. Now, if you're decaying, the rate is negative. If you're growing like money, the rate would be positive. Continuing this problem, we know that the wood contains about 1.67% of the original. So if my original is A naught, I'm going to end with 0.0167 of A naught. Cancel out the A naughts, ln both sides, divide away that long decimal, and you'll get 33,000 years. And then finally, Newton's law of cooling. So in Newton's law of cooling, we have this formula. T is the temperature of the surrounding medium, or the air, or the surrounding water, whatever your word problem, the context of the word problem. U naught is the heated temperature's initial temperature, and U of little t is the temperature at any time little t. So U of t is the temperature of the object at any specific time. Capital T is the surrounding temperature. U naught is the initial temperature. K is the rate. Little t is the time. So I have a cake, and it's 350 degrees, and it's cooling in a 70-degree room. The cake reaches 300 degrees Fahrenheit in 5 minutes. When will the cake reach 200? Okay, forget about the 200 for right now. So I have my initial temperature. So U naught is 350. U of 5 is 300. In 5 minutes, the cake is 300. So that means U is 300 and T is 5. The surrounding temperature is 70. So I'm going to list my formula and the variables that I've been given. And I'm going to plug them in. 300, 70, and so on. Okay, now it's time to solve. 350 minus 70 is 280. I'm going to subtract this 70 from both sides, divide by the 280, take the natural log, see what that is on my calculator, and then finally divide that answer by 5, and I get the rate, the cooling rate, right? So what we want to do with Newton's law of cooling is take the first piece of information and actually find the rate that the cake is cooling. If I don't want to do all this by hand, I can do y1, y2 from this equation right here and intersect, and you can see I get the rate on my calculator. So by hand or on your calculator, it's completely up to you. Now that I know my rate, I want to know that when the cake is going to be 200 degrees. So I'll plug 200 degrees in. The air temperature was 70. The original was 350. And now I know my rate, Y1, Y2. I used this window and I intersected. And once I pull it out of the oven, it's going to take about 19.5 minutes to cool down to 200 degrees. Okay, that's it for exponential and logarithmic functions. And you guys, good luck on your quizzes.